Well, hi everyone, my name is Ken Hongshen. I'm a PhD student at UT Austin, and today I would like to present our research titled Control of Vertical Support and Frontal Plane Stability during Perturbation-Induced Single Support in Individuals Post-Stroke. So walking ability is an important predictor of quality of life after stroke, and difficulty in supporting the body weight with their paretic limb is a typical gait impairment after stroke. For example, on the animation, you can see a shorter arrow on the left side, indicating less weight bearing with a paretic limb. This is more obvious in those stroke survivors who have limited capacity in walking in the community, that they cannot bear 100% of body weight during walking. This reduced weight bearing also is associated with forward propulsive force during gait that affects walking speed. In addition to reduced weight bearing, stroke survivors also have reduced time spent on the paretic limb during walking, and this asymmetric single stance duration appears to be associated with ambulation independence. So as this impairment in paretic single stance appears to be a critical element that affects walking ability after stroke, there is a need to identify the specific deficits that cause this impairment, so we can then develop a targeted intervention to improve single support ability and that leads to better walking performance. However, the specific origin of the impaired paretic single support during gait remains largely unknown. This is partly because of the confounding factors that are inevitable when studying continuous gait in individuals post-stroke. For example, during gait, they show several global abnormalities including asymmetric weight bearing, single support duration, and foot placement. So even if, say, we found a reduced joint moment during gait, it is hard to determine whether this is a primary cause of impairment or secondary to those inherent test abnormalities. So to provide more direct evidence by removing those confounding factors, here we propose a perturbation approach that could induce single support and allows us to study the task in a more controlled manner. Here is an animation of the perturbation. When the participant stands on a perturbation platform, we monitor their initial weight bearing to make sure the body weight is evenly distributed between limbs. And at an unpredictable timing, we remove one of the support surface by dropping it vertically. After the drop, the limb that is not dropped will have to support the body weight as a single support limb. And on the right side, you can see how that looks like in the lab. So the platform drops 4.3 centimeters. It takes 94 milliseconds for a free-falling object to drop the same distance. And the single support limb will reduce the downward acceleration by providing upward force. So our perturbation induces a single support duration that is more than 94 milliseconds. Although the interval is shorter than that during gait, this is similar to the required single support duration to successfully execute a predicted step after experiencing a slip. So this is still a functionally meaningful duration. And during the single support phase, intuitively the leg extensors have to activate it to provide vertical support. And when stroke survivors are performing leg extension like ankle plantar flexion or hip extension, they typically show an abnormal activation at the hip adductors. This abnormal synergistic activation may have negative consequences during single support phase during gait. For example, excessive hip adductor moment during single support phase will accelerate the pelvis downward, which disrupts the ability to provide vertical support. Also, this excessive hip adductor moment will limit the ability to generate medial grunction force, which will cause a higher moment arm between the grunction force to the body center mass and thus increase angular momentum of the body. This will destabilize the body. So based on those information, we hypothesize that when we induce single support to individuals post-stroke with perturbation, they will show an excessive hip adductor moment at the paretic side. This will lead to a reduced vertical support and stability. And we also hypothesize that vertical support and stability found during the perturbation will be associated with spatial temporal gait performance. So we have recruited 12 participants with chronic stroke. The experimental protocol comprised of two elements. So first they walk on the walkway to record their spatial temporal gait parameters. And after that, they stood on a perturbation platform, and at an unpredictable timing, we randomly drop one of the platform. So there are in total 5 perturbations delivered to each limb, and we calculate our outcome measures within 94 milliseconds, defined as a single support interval. And based on our hypothesis, we have 4 primary outcome measures, including the hip torque on the frontal plane, vertical support, stability, and those association between the parameters and the gait performance. So we found that right before the perturbation onset, their paretic side already showed a higher hip adduction torque when standing still with even weight distribution between limbs. And this carried over to the single support phase, that their paretic limb had difficulty generate abduction torque, while the non-paretic limb could do that. So they basically generate different direction of hip torque in the frontal plane between paretic and non-paretic limb. Next, we want to see if this abnormal hip torque disrupts the vertical support. And we use stiffness on the vertical direction to quantify vertical support. We plot on the top graph, you can see plot out the vertical displacement of the center of mass and the vertical gruntion force beneath the single stance limb. Calculate stiffness as the slope of the regression line, and the average R-square is more than 98% for both limbs, indicating a good fit. And we found that the paretic limb did have reduced vertical support compared to the non-paretic side, as we hypothesized. We then quantify stability using total angular impulse caused by the gruntion force to the body center mass. So we took the cross product of the gruntion force and the moment arm, and we integrated over time during a single support interval. We found that a higher angular impulse during paretic single support, indicating reduced stability. We then want to see if the abnormalities observed during perturbation task is really associated with gait. We first look at whether the single support duration during gait correlates with vertical support during perturbation. We found that when walking at self-selected speed, single support duration at the paretic limb positively correlates with stiffness during perturbation-induced task. And this positive correlation was also found when walking at their maximum walking speed. We then look at whether the stability during perturbation-induced single support correlates with step width during gait. However, we didn't find any associations here. So lastly, we want to see if the vertical support and stability at both paretic and non-paretic limb during perturbation-induced single support could predict their walking speed. So we used stepwise linear regression to find the primary predictors. We found that paretic stiffness is the only predictor of self-selected walking speed, which explains about 36% of the variance in walking speed. We then try to predict their fastest walking speed, and we found that stiffness at both paretic and non-paretic limb were both significant predictors, and the stiffness at the non-paretic limb negatively associates with fastest walking speed. This is not very intuitive because we expect higher support to be beneficial for walking, but this could also due to overcompensating from the non-paretic side. And if that's the case, maybe asymmetry would be sufficient to explain the variance of walking speed. So we quantify asymmetry by subtracting non-paretic stiffness from the paretic side, and we put all three predictors into a regression model. We found that after including asymmetry as a predictor, the stiffness at the individual limb did not have unique contributions to explain any more variance. And the asymmetry of stiffness explained about 75% of the variance in fastest walking speed in individuals post-stroke. So to wrap up, we found that during perturbation-induced single support, the paretic hip joint did produce excessive adduction torque. This likely caused reduced vertical support and stability in our result. And the vertical support during the perturbation-induced task appears to be an important element that relates to walking performance. So specifically, the paretic vertical support during perturbation-induced task associated with paretic single support duration during gait, and that predicts self-selected walking speed as well. And the asymmetry of stiffness between paretic and non-paretic limb predicts fastest walking speed after stroke. So in the future, we will investigate whether we could apply functional electrical stimulation to the hip abductors to improve single support performance. And we'll also investigate whether we could use repetitive perturbation as a training tool to improve their single support ability. So thank you for your attention. This is a collaboration between UT Austin and University of Maryland. And I would like to acknowledge all my colleagues who helped with the project. Now I will happy to take any questions you have.